thing I want to talk to you about is, well, it's kind of interesting. It's more theoretical than practical, but I think it's an interesting thought experiment, and that's called guarded commands. So what guarded commands are, well, let me show you. So here's an interesting piece of code. If x is greater than or equal to y, then max is equal to x. Else max is equal to y. Else if y is greater than or equal to x, max is equal to y. Okay, so this is interesting. It's a little strange, right? Does it really matter if x is greater than or equal to y, or y is greater than or equal to x when y equals x, right? If y is equal to x, does it matter which of these if statements gets executed, this one or this one, right? The net effect, setting max equal to x or max equal to y, it's the same effect, right? But you know deterministically that what is going to get executed is the code in this block, because that's the first thing that the program is going to encounter as it runs through the code. It's going to encounter that first if statement before it encounters the else if statement. All right, so what are some things that I can say about this? Well, first of all, this is deterministic. And here, it really doesn't matter. Which of those two lines of code gets executed when x is equal to y. So there is a kind of a funky language element that's been proposed called a guarded command. All right, so let's take a look at it. So a guarded command looks like this. If x is greater than or equal to y, then max is equal to x. Y is greater than or equal to x, then max is equal to y. So this is called a guard. Now, the way this works is if x is equal to 5 and y is equal to 4, then max equals x gets executed because x is greater than or equal to y. So deterministically, you can be sure as long as x is greater than y, max equals x is going to get executed. Likewise, if x is equal to 4 and y is equal to 5, well, then this is going to get executed. Because again, that makes sense, right? If y is bigger than x, then max is equal to y. Now, when x is equal to 5 and y is equal to 5, well, now we have an interesting situation. Because either we can say max is equal to x, or we can say max is equal to y. So what will happen is that one of these two is randomly selected. All right, so how does this work a little, like conceptually, right? So, well, I guess I basically explained that, but you might be wondering, well, what about situations where, I don't know, where we don't have something that's mathematically true, where it really doesn't matter whether y is equal to x. It really doesn't matter which one of these statements gets executed if y is equal to x, right? But what if y is not equal to x, but we still have a situation where we want to execute code max equals y or max equals x? In other words, for whatever reason, it just doesn't matter whether we set max equal to x or max equal to y, as long as y is greater than x, for example, or equal to x, or not equal to x. I mean, it doesn't matter. We can set up any criteria we want. So the way the guard works is if this statement is true and this statement is true, one of the two statements, max equals x and max equals y, gets randomly selected. So you can put anything you want in these two statements here. But if one is true and the other isn't true, then the code associated with the one that is true will get executed. If they're both true, then one of these two gets randomly selected. All right, that takes care of guarded commands. Now, one last thing that should have made its way into the lecture from last week, but didn't, and that is I just want to make sure I've explained short circuit evaluation. Because, and I think I started to explain it last class, but I was more talking about functional side effects. So I want to make sure you understand the difference, or not the difference, but you understand what short circuit evaluation is. So consider this expression. A is greater than or equal to 0, and B is less than 10. All right. So do we always have to evaluate B is less than 10? I mean, think about it. From a performance standpoint, do we always have to evaluate B is less than 10? And the answer is no, we don't, right? If this evaluates to false, then we don't bother with we're not going to bother with B is less than 10. Okay? It's not worth bothering, right? This is false. So the whole expression, false and whatever this is, whatever B evaluates to, is going to be false. So where could that be useful? That's present in some languages, but not all. So where could this be useful? Well, it could be incredibly useful in this kind of situation. Take a look at this loop. Index equals 1. And then I say, while index is less than length, and list sub index is not equal to the key, then index plus plus. So what's happening here? Well, what's happening here is we're checking two different Boolean expressions, and we can use short circuit evaluation to avoid something horrible happening. So what is the horrible thing that we want to avoid? Take a moment, hit pause, and see if you can figure it out. Okay, what's the horrible thing we want to avoid? Well, take a look at this. Index less than length. So if index is equal to length, then if we say list sub index, we're going to have an out of bounds error, right? So if we don't check this in order, or let me rephrase that. If we have to check both of these Boolean expressions to determine whether the expression is false, we're going to have a problem. So what's awesome about the way this Boolean expression is set up is it uses short circuit evaluation. The moment that index is equal to length, this expression is false. All right? If we were to try to take lists of index or lists of length, that would be an out of bounds error in many C-based languages. So I'll just write that down. When index is equal to length. When index equals length, we're out of bounds. So what's going to happen here is when index is equal to length, this expression will evaluate to false, and we won't evaluate this part of the expression, so we won't end up with an index out of bounds error. So that's awesome. Now, if we change the order of this, if we did lists of length not equal to key, check that first, or lists of index not equal to key, check that first, and then did index less than length, that might be, from a Boolean algebra standpoint, perfectly fine. There's no reason why you can't do things in a different order. And if we had some code that was like super smart, maybe we were able to break up these Boolean expressions and evaluate them in parallel to speed up the evaluation of a Boolean expression. That might be super smart too, but we could run afoul of this problem. So here we can just take advantage of short circuit evaluation and avoid this index out of bounds error. Okay, so it turns out that some languages allow you to have the choice of whether you want to do short circuit evaluation or not. So that's kind of cool, because if we had some system that was like a super powerful parallelizing compiler that would look at statements and say, well, I can evaluate this statement at the same time I'm evaluating this other statement, so we could quickly get to the bottom of evaluating Boolean expressions in a smaller Boolean expressions in a larger Boolean expression. That would be really cool. Again, we have that short circuit evaluation problem. So maybe there's some way we could indicate to the compiler, hey, don't evaluate this expression in parallel, evaluate it in order. So it turns out that Ada has that ability. So this is C-based. And let's take a look at how Ada would attack this. So the way Ada would attack this is it would say, while index is less than or equal to length, and then list sub index is not equal to key. Loop index equals index plus 1. End loop. So that's pretty cool. So we have this then, and the then indicates, hey, guess what? We would like this expression to be evaluated first, and then this expression. It's implied up here. This expression gets evaluated first, and then this expression. But here we're being explicit about it. So we're saying use short circuit evaluation. Okay, well, that ends our discussion of control flow.